Before a commercial aircraft ever pushes back from the gate, it requires the processing of an immense volume of raw data. We're talking thousands of pages of permanent infrastructure manuals, dynamically shifting weather models, and time-critical hazard notices scattered across the globe. Yet, in the cockpit, this overwhelming flood of noise is distilled into a few highly structured pages, a clean Jeppesen approach plate, and a standardized ICAO flight plan. The process that bridges the gap between theoretical data and real-time cockpit execution is called aeronautical information synthesis. It is the rigorous translation of global infrastructure geometry, temporary regional hazards, and the physical limits of the aircraft into a precise, executable four-dimensional trajectory. Methodical. To understand how this works, we first have to master the baseline structure of aeronautical data, the permanent architecture that dictates global airspace. Next, we have to look at how that dense raw data is translated into tactical charting, specifically the Jeppesen Index, for high-workload cockpit environments. Finally, we have to encode that physical intent into the ICAO standard flight plan, interfacing directly with air traffic computers. This synthesis converts static, text-based rules into a dynamic digital plan, recognized by global air traffic systems, providing the necessary bridge between a stack of infrastructure manuals and an active, managed trajectory. The foundation of all permanent aeronautical data is the Aeronautical Information Publication, or AIP. Published by individual state civil aviation authorities, this document compiles the permanent rules and physical layouts of a country's airspace. To allow rapid cataloging, the AIP is divided into three standardized color-coded sections. Part 1, General, is highlighted in light blue. Part 2, En route rules and airspace classifications, is green. Part 3, Aerodromes, detailing runway dimensions and ground movement, is yellow. While the AIP serves as the permanent foundation, temporary operational updates or explanatory notices require a separate channel. These are published as Aeronautical Information Circulars, or AICs. Because dispatchers and pilots must process these updates rapidly, the International Civil Aviation Organization mandates that AICs be color-coded by subject matter. This standardized system allows for immediate cognitive sorting by the flight crew. Pink AICs demand mandatory review, as they cover crucial flight safety and accident prevention notices. Yellow circulars detail operational matters, directly impacting communication protocols and ATC facilities. White circulars handle administrative logistics, like fee structures or licensing. Mauve circulars dictate temporary airspace restrictions, like military exercises that require specialized en route clearances. Green circulars provide updates and corrections to aeronautical maps and charts. The final layer of the architecture handles the most dynamic variables. Notices to air missions, or NOTAMs, are issued exclusively for short-notice, time-critical hazards. If a runway is unexpectedly closed for emergency maintenance, or a critical navigation beacon suddenly fails, that information moves through the NOTAM system to intercept pilots during pre-flight or en route planning. Historically, domestic NOTAMs utilized a heavily abbreviated single-line format that was notoriously difficult to read. The aviation industry is actively transitioning to the standardized ICAO format, which breaks the data into organized multi-line blocks. The ICAO format parses the hazard into highly structured fields. It begins with the Q line, a coded string that immediately identifies the flight information region and the exact subject matter being reported. Subsequent fields, labeled A through E, drill down into the specifics. They define the precise geographic location, the exact start and end times in Universal Coordinated Time, and provide a plain text description of the operational limitation. By structuring permanent infrastructure, temporary updates, and dynamic hazards into this rigid hierarchy, crews ensure they have a complete, unbroken picture of the airspace before they ever initiate an engine start. But having access to this data isn't enough. Raw AIP documents are far too dense and text-heavy to be processed by a pilot during the high-workload tactical phases of flight. To solve this, the commercial aviation industry relies on routing manuals, most notably the Jeppesen Airway Manual, to declutter and restructure state-published data into standardized templates. Jeppesen utilizes a strict spatial indexing system. Rather than burying airport data in alphabetical lists, they are cataloged geographically by city, grouping primary and secondary airfields together within a terminal area. The numerical syntax is highly intentional. A primary airport receives a round index number ending in 0, like 10 or 20. The numbers following the dash represent specific page types, with the 10-9 page universally recognized as the primary airport diagram. Approach plates scale up sequentially from index 11. An 11- series will cover ILS approaches, while 12 or 13- series might cover GPS or VOR procedures for that same runway. This document layout outlines the heading and briefing information sequence for a standard instrument departure or arrival. The primary communication frequencies, final approach course, and minimum altitudes are always sequenced at the top in the exact order they will be used by the crew. Looking at this graphical-to-scale depiction area, we see Jeppeson's core charting philosophy. Whenever possible, departures and arrivals are printed to scale to immediately enhance spatial awareness as the route intersects physical nav aids. To reduce cognitive load when cross-referencing vertical profiles, all altitude constraints on the plan view are strictly color-coded in blue. The line symbology around these blue numbers dictates the physical constraint. A line both above and below the number indicates a mandatory crossing altitude. A line only below means an at or above restriction, and a line only above signifies an at or below restriction. Overlaid directly on this plan view is the magenta minimum sector altitude, or MSA circle. Referencing the primary nav aid, it guarantees a minimum of 1,000 feet of obstacle clearance within a 25 nautical mile radius for each specific directional sector. Beyond the terminal environment, en route charts utilize grid MORAs, minimum off-route altitudes. Plotted in gray within each latitude and longitude grid, they guarantee 1,000 feet of obstacle clearance in normal terrain and 2,000 feet of clearance over designated mountainous boundaries. The Jeppeson chart topology is a highly engineered cognitive tool. It translates dense state regulations into immediate spatial situational awareness, allowing crews to navigate complex airspace without reading paragraphs of text. Once the physical routing is verified against the tactical charts, that intent must be communicated to Global Air Traffic Service Automation. This is achieved through the ICAO Flight Plan, Form 7233-4. It serves as the standardized alphanumeric interface between the cockpit's planned trajectory and ATC computers. In Item 9, operators are legally required to encode the physical aircraft type and its wake turbulence category. Heavy aircraft generate immense, dangerous wake vortices, and ATC computers need this data to sequence following aircraft safely. Historically, ICAO relied on legacy categories based strictly on an aircraft's maximum certified takeoff mass. Modern airspace, however, is transitioning to wake turbulence groups, or WTG. This matrix of wake turbulence groups shows how the modern system accounts for specific wing characteristics and aircraft resistance profiles. The blue cells highlight where these refined metrics safely reduce separation minima between specific aircraft pairings, increasing runway throughput. In Item 10, the equipment codes begin. Field 10A dictates the aircraft's communications, navigation, and approach aid capabilities. This alphanumeric string tells the ATC computer if the aircraft qualifies for strict performance-based navigation routing. Field 10B dictates surveillance capabilities. This tells ATC exactly what secondary radar transponder and automatic dependent surveillance broadcast, or ADSB equipment, is actively transmitting from the airframe. Item 15 defines the route. Here, expected cruising speeds cannot be arbitrary. They must be encoded strictly as true airspeed in knots, preceded by an N, or as a Mach fraction, preceded by an M. The requested cruising levels in Item 15 must also comply with global hemispheric or semicircular rules. Depending on the magnetic track of the flight, altitudes are restricted to specific odd or even flight levels to guarantee safe vertical separation between opposing traffic. When filing en route delays, the syntax changes based on airspace. Internationally, delays are filed in Item 18 using the DLE prefix. Domestically, within the U.S., ATC computers process delays using oblique strokes filed directly within the Item 15 route string. Item 19 handles supplemental information, things like aircraft color, life jackets, and survival radios. This data is not transmitted to active air traffic control. It is retained exclusively by the filing facility to streamline search and rescue operations if the aircraft goes missing. The most critical entry in Item 19 is total fuel endurance. This requires aggregating the planned trip fuel, the required contingency fuel, and the legal reserve fuel into a single 4-digit time value. A legally filed ICAO flight plan is a highly compressed data packet. It dictates exactly how the ATS system will separate, sequence, and protect the aircraft from departure to destination. Every alphanumeric entry on this form traces back to the raw data we started with. The Item 15 route is derived from the Jeppesen Index. The Item 18 remarks account for active NOTAMs. The Item 19 endurance proves the aircraft meets the physical limits required by the AIP. The flight plan is the final standardized expression of a legally verified safe trajectory. Flight planning is the continuous management of the delta between permanent publications and real-time operational reality. Air traffic service automation relies entirely on this baseline of synthesized data to function safely. If the inputs are wrong, the computer will route the aircraft into conflict. Critical in-flight decisions, such as fuel management calculations and the plotting of contingency equal time points over oceans, are only as accurate as the pre-flight synthesis that generated them. True professional airmanship requires mastering this entire architecture. By pulling the right data from the AIP, translating it through tactical charts, and encoding it correctly for ATC, crews guarantee a safe, executable 4-dimensional trajectory before the engines ever start.